Today we're going to look at a really interesting and intricate integral, and it involves lots of really nice tricks. So the integral in question for today is the integral from 0 to infinity of the natural log of x over 1 plus e to the x. And before we get started, I'm going to evaluate this limit kind of on its own because it's one of the last steps, and I don't want to take away from the momentum of finishing the problem off. So we'll start by showing that the limit as epsilon goes to 0 from above of the natural log of epsilon times the natural log of 1 plus e to the minus epsilon all over 2 is equal to 0. Okay, so let's notice over here that this is an indeterminate form, and it's an indeterminate form of type infinity times 0. And why is that? Well, that's because this natural log function trends towards negative infinity as epsilon trends towards 0 from above, whereas this trends towards the natural log of 1 plus 1 over 2, in other words, the natural log of 1, which is 0. So that makes it, like I said, an indeterminate form of type infinity times 0. So we can rewrite this into an indeterminate form that we can use L'Hopital's rule on fairly easily. So we'll write this as the limit as epsilon goes to 0 from above of the natural log of 1 plus e to the minus epsilon over 2 over 1 over the natural log of epsilon. And now let's observe that this is of type 0 over 0. Which means we can apply L'Hopital's rule. So let's do that. So let's say this equality right here is applying L'Hopital's rule, which means we need to take the derivative of the numerator and the denominator. So keeping in mind the chain rule, the derivative of the numerator will be 2 over 1 plus e to the negative epsilon times, let's see, e to the negative epsilon over 2. That's the derivative of the natural log function, takes the reciprocal, and the derivative of the inside is, as I've written. And I've just noticed that I missed something. There should be a minus sign here as well, because the derivative of e to the minus epsilon will involve a minus. Now let's take the derivative of this 1 over the natural log of epsilon. We can do that again with the chain rule. That'll end up with negative 1 over the natural log of epsilon squared times 1 over epsilon. Now let's notice some minus signs cancel, which is nice. It's really inconsequential because our limit will be 0, but it does make it a little bit less annoying to work with. So I'll cancel those to a plus. And then I'll also do a bit of a trick where I evaluate this limit partially. And this may seem a little bit sketchy, but if you were to look at where we are going and rewrite this as the product of two limits which we know exist, it's actually okay. So notice as epsilon goes to 0, this term right here trends off to the number, let's see, 2, whereas this right here trends off towards the number 1. That's because e to the 0 is 1. Then some of those zeros cancel. So notice this, some of those 2's cancel. This 2 will cancel with this 2. And then let's see, what does that leave us with? So now we'll have a 2 left over. I can bring that out, and that's in fact in the denominator. Let's maybe move that down here. We have a 1/2, and then the limit as epsilon goes to 0 from above. And then maybe the best way to write this is as the natural log of epsilon squared over 1 over epsilon. And now notice that this is another indeterminate form. Well, perhaps it's the... And now let's notice we have an indeterminate form again. And what type is the indeterminate form here? Well, it's type infinity over infinity. Because as epsilon goes to 0 from above, the natural log squared will go to positive infinity, whereas the denominator will also go to positive infinity. So now perhaps we'd like to use L'Hopital's rule again, and that's exactly what we'll do. So again, being careful with the chain rule and the definition of those derivatives, what will we have? So for the numerator, we'll have 2 times the natural log of epsilon times 1 over epsilon. And then for the denominator, we'll have negative 1 over epsilon squared. So let's see. This 2 here will cancel this 2 here. And then this epsilon here will cancel this epsilon squared down to just a single epsilon. And let's notice it is again an indeterminate form of type infinity over infinity, which means we should apply L'Hopital's rule one more time. So let's see, that'll leave us with the limit as epsilon goes to 0 from above, and then we'll have 1 over epsilon in the numerator and negative 1 over epsilon squared in the denominator, but actually some minus signs cancel, leaving us just with epsilon squared like that. Okay, but now a little bit of simplification will show us that we have the limit as epsilon goes to 0 from above of epsilon, which is 0. But that's exactly where we wanted to get on this. And there we have it. And now let's introduce a little bit of notation that'll help us out. Let's set I of epsilon equal to the integral of the same function from epsilon to infinity. And notice under this new notation, our goal integral, which I'll call I now, is equal to the limit as epsilon goes to 0 from above of I epsilon. Okay, so now I think we're set up nicely to really get started here. So let's move with this. So this will be the limit as epsilon goes to 0 from above of I epsilon. But I'll in fact manipulate this a little bit, maybe by multiplying the numerator and the denominator by e to the minus x. So that'll leave me with the integral from epsilon up to infinity of e to the minus x times the natural log of x over 1 plus e to the minus x dx. Okay, so there we have that. And now let's perform an integration by parts here. So let's set u equal to the natural log of x. Notice that implies that du is equal to, let's see, 1 over x dx. And then next up, we'll set dv equal to all of the rest of the stuff. So this will be e to the minus x dx over 1 plus e to the minus x. And the motivation here is that we see the derivative of the denominator is inside of the numerator. Well, up to a sign, I should say. That means that this thing has a nice antiderivative, which is minus natural log of 1 plus e to the minus x. And that sorts out our whole integration by parts setup. So let's see what that does to our integral. So we'll have u times v evaluated at the endpoints. So let's see, carrying the limit through, we have the limit as epsilon goes to 0 from above of minus the natural log of x times the natural log of 1 plus e to the minus x. And then we'll have minus the integral of v du. But notice our v has a minus sign built in, so those will cancel to a plus. And we'll have plus the integral from epsilon up to infinity of natural log of 1 plus e to the minus x over x dx. Okay, so I think that's looking good so far. And now from here, inside of this natural log, I'm going to multiply by a special version of 1. And that version of 1 will be 1 minus e to the minus x over 1 minus e to the minus x. And let's see where that'll leave us. So bringing all this down, we have the limit as epsilon goes to 0 from above. We have minus natural log of x times natural log of 1 plus e to the minus x. That's evaluated from epsilon up to infinity. We'll actually take care of that evaluation at this next step. And then we have plus the integral from epsilon up to infinity of, let's see, 1 over x. And then multiplying these together, we have 1 minus e to the minus 2x over 1 minus e to the minus x dx. Okay, good. And now before moving on to the next step, let's get the evaluation of this taken care of. So notice if we set x equal to infinity, obviously that's like taking the limit as x goes to infinity. We get the natural log of infinity times the natural log of 1, but that's an indeterminate form of type 1 times infinity. And in fact, the evaluation of that portion is almost exactly like taking this limit right here, so we'll leave that out. So that only leaves us with what happens when we plug in epsilon, but we haven't taken the epsilon limit yet, so we just get, well, this thing evaluated at epsilon. But since that's the lower bound of integration, the minus sign will like cancel out. So all of that is to say that we get this sort of object. We'll get the natural log of epsilon times the natural log of 1 plus e to the minus x. And now that's not exactly what we have right here, but it's like kind of ramping up to be fairly similar. Notice that this is not an indeterminate form at the moment. If we take the limit as epsilon goes to 0, this goes to infinity, whereas this goes to natural log of 2. So that's divergent at the moment, but you have to keep in mind that what we're really doing is taking the limit of this whole thing, which involves this integral over here. So in fact, there'll be a portion of this integral that will help tame the divergence of this. It'll turn it into this thing over here, as we will see in a future step. Okay, so what's our next game? So I'll copy a bunch of this stuff down, and then we'll get going on that. So I have this natural log of epsilon, natural log of 1 plus e to the minus epsilon. And then I'll break these into two integrals. And that's because I've got this natural log of a quotient, which will turn into the difference of natural logs. So maybe we'll fit this in as the integral from epsilon up to infinity of natural log of 1 minus e to the minus 2x over x dx, and then minus the integral from epsilon up to infinity of natural log of 1 minus e to the minus x over x dx. Okay, good. And now I'm going to sneak in a 2 right here. So multiply by 2 and divide by 2. That makes this denominator match exactly with that exponent right there. And that actually motivates us a change of variables. And I will call this over here maybe integral 1. And I'll call this over here integral 2. Because we're going to use the same variable for the change of variables in both of those, but I want to distinguish them. So in this first integral, we'll take the change of variables given by t equals 2 times x, which tells us that dt equals 2 dx. And then furthermore, when x is equal to epsilon, that tells us that t is equal to 2 times epsilon. And then for this second integral, we'll take the trivial substitution, which is just t equals x. And that essentially looks like it doesn't do anything, but it changes the dummy variable from x to t. So let's see where we are after that. So bringing this down, we have the limit as epsilon goes to 0 from above, natural log of epsilon, natural log of 1 plus e to the minus epsilon. And then this first integral will turn into the integral from, let's see, 2 epsilon up to infinity of the natural log of 1 minus e to the minus t over t dt. Okay, so like I said, that's what the first integral turns into. And then the second integral, well, it's going to look pretty much exactly the same, except the x's and the t's will swap. So we'll have minus the integral from epsilon up to infinity of the natural log of 1 minus e to the minus t over t dt. Okay, so I think we're in a pretty good spot. Maybe I'll do one partial step right here, and we'll start with the full step at the top of the next board. Notice that since we're integrating the same function there over really complementary bounds of integration, we could change this into the integral from epsilon to 2 epsilon of all of that stuff dt, as long as we put a minus sign out front just to sort out the order of integration there. And that's exactly where we'll start the top of the next board. So just to reiterate, we'll have the limit of this object minus this integral here. So this is where we left ourselves. Now I'm going to take this integral that we just ended with and perform another change of variables to get epsilon out of the bounds of integration. And this change of variables will be to set t equal to epsilon times x. But notice that that means that dt is equal to, let's see, it'll be epsilon dx. Furthermore, when t is equal to epsilon, we see that x is equal to 1. And when t is equal to 2 epsilon, we see that x is equal to 2. So I think this has a really nice calming effect on this integral. Okay, so let's go from there. I'll bring down a bunch of stuff real quick. Maybe we'll speed through this. And then we'll have minus the integral from 1 to 2 of the natural log of 1 minus e to the minus epsilon x over x dx, where the epsilon that we picked up from the dt cancels for the one with the t right there. Okay, nice. And now we're going to do a simplification using the power series of e to the x here. So let's maybe quickly notice that this thing cancels out using the fact that e to the minus epsilon x is equal to the sum, as n goes from 0 to infinity, of minus 1 to the n epsilon times x to the n over n factorial, which is in fact equal to 1 plus the sum as n goes from 1 to infinity of that same thing. That's because the first term of the exponential function will be 1 when we have that sort of setup. But now that 1 will cancel with the 1 right here and leave us with something which is a little bit easier to work with. So let's write that out. Again, bringing a bunch of stuff just down, we'll have now inside of the natural log will be something like this. Epsilon times x, and then 1 minus epsilon times x over 2 factorial plus epsilon times x squared over 3 factorial minus ... That's an infinite sum. And this is all over x dx. Okay, good. And so again, that's from simplification of this object right here where we factored out like a greatest common factor. Okay, but what can we do from here? Well, notice that this is really the natural log of a product of things. We have epsilon times x and then the rest of this stuff. So we can split up the natural log of a product into the sum of natural logs. Okay, so again, bringing all this down, we will now have minus the integral from 1 to 2 of the natural log of epsilon x over x, and then minus the integral from 1 to 2 of the natural log of, let's see, it'll be 1 minus epsilon times a bunch of stuff. And I'll just put all of that stuff into this blue and yellow box. And this is all over x dx. Okay, so that's where we are at the moment. But now we're going to do something that looks ahead to a future calculation. We'll see that this limit here exists. And by this limit here, I mean the thing involving these first two terms and this second integral. Furthermore, this limit over here exists. That means that we can break them into the sum of two limits. But then what's this limit over here that I'm maybe putting this magenta box around? And so this is, of course, taking epsilon to 0 from above. Well, we can do some quick bounding and see that it's actually possible to bring this epsilon limit inside of the integral, which means this stuff right here is trending off towards 1. But if that stuff right there is trending off towards 1, the natural log of 1 is 0. So that means all of this stuff in the magenta box is trending off towards 0. Which means all we're left with is the limit of all of this stuff underlined in blue. So now let's get to that. So this is where we left off at the bottom of the last board. And now I'd like to note that this natural log of epsilon times x, again applying a logarithm rule, can be written as the natural log of epsilon plus the natural log of x. And then we can split that into two integrals. And so we don't take up any room, let's maybe do that now. Okay, so there we have it. Now we're ready to do our last steps. Okay, so let's do those. Bringing all of this stuff down for one of the last times, what do we have? So let's see. We'll have minus natural log of epsilon, and then this first object integrates out quite nicely. So notice that'll give us the natural log of x evaluated from 1 to 2, which will in the end give us the natural log of 2. Okay, so let's see. We've got the natural log of epsilon times the natural log of 2 right there. And now for this next one, perhaps we'd like to do a u substitution. So let's do that. Let's set u equal to the natural log of x, which makes du equal to dx over x. Furthermore, let's notice that when x is equal to 1, we have u is equal to 0. Whereas when x is equal to 2, u will be equal to the natural log of 2. So that sorts out our change of variables for this second integral. So that'll allow us to write this as minus the integral from 0 up to the natural log of 2 of u du. Great, and all of that is still within this limit. Okay, so now let's peer into these first two terms. And notice these first two terms both have a natural log of epsilon. But not only do they have a natural log of epsilon, but they've got another natural log type term with a difference between them. That means we can factor out the natural log of epsilon and then combine the purple underlined things using logarithm rules. So finally we're changing some things. Got the limit as epsilon goes to 0 of the natural log of epsilon times the natural log of 1 plus e to the minus epsilon over 2. So this green stuff turned into this green, and then that purple underlined stuff turned into this stuff that I'm underlining in purple. Okay, but that's actually in a closed off limit at this stage. And that's because there's no epsilon over here that we need to worry about. So now we can essentially just integrate that out and evaluate it at the limits. So that'll give us minus u squared over 2 evaluated from 0 to 2. And now let's look in at this. And notice that this limit that I have in these blue parentheses is exactly our tool that we calculated before. And the value of this limit was 0. Well, I guess it still is 0. So that means we can take this limit to 0, and then we do this evaluation over here. That should have been a natural log of 2, ending with minus 1/2 times the natural log of 2 all squared. And that's the final value for our calculation. Now I've done lots of nice, complicated, interesting integrals on the channel. There should be one on the screen right now if you'd like to check it out. And that's a good place to stop.
Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.